The James Webb Space Telescope, humanity's most advanced space observatory, stands today as a monumental achievement in the pursuit of cosmic understanding. Tasked with uncovering the deepest secrets of our solar system and distant galaxies beyond, it continues to redefine our perception of the universe and our place within it. Recently, scientists turned the telescope's powerful gaze toward a star system located approximately 120 light-years away from Earth. What they found has sent waves of excitement and intrigue through the scientific community. The telescope detected compelling evidence of carbon-based molecules in the atmosphere of a distant exoplanet, strongly suggesting it may be an ocean world. An extraordinary revelation that deepens the mystery surrounding potentially habitable planets beyond our solar system. The exoplanet in question is K2-18b, a celestial body that has already intrigued astronomers for years. This new discovery has only intensified interest in the planet, as it offers the tantalizing possibility of life-supporting conditions. K2-18b orbits a cool red dwarf star known as K2-18 in the constellation Leo and lies comfortably within its star's habitable zone, a region where conditions may permit the existence of liquid water. This super-Earth, about 8.6 times the mass of our own planet, occupies a unique category of exoplanets that fall between the size of Earth and Neptune, a planetary class conspicuously absent from our own solar system. That uniqueness alone makes K2-18b an object of considerable interest. But what truly sets K2-18b apart is the composition of its atmosphere. Using its unmatched infrared sensitivity, the James Webb Space Telescope has identified the presence of carbon compounds, specifically methane and carbon dioxide, within K2-18b's atmospheric envelope. This points to the possibility of a hydrogen-rich atmosphere overlaying a planet covered in oceans, a configuration that could support life, or, at the very least, the kind of chemistry associated with it. This discovery builds upon earlier data, obtained by NASA's Hubble Space Telescope, which first offered a glimpse into K2-18b's atmosphere and opened the door for more in-depth analysis. However, while Hubble laid the groundwork, it is Webb's cutting-edge spectrographic capabilities that have delivered the most detailed atmospheric reading of a habitable zone exoplanet to date. One of the most intriguing aspects of the new findings is the potential presence of dimethyl sulfide, ADMS, a molecule that, on Earth, is predominantly produced by marine organisms, particularly phytoplankton. Although evidence of DMS in K2-18b's atmosphere remains tentative and unconfirmed, the very suggestion of a biosignature gas being detectable from such an incredible distance has electrified researchers across disciplines. If validated, it would mark an unprecedented leap forward in our search for extraterrestrial life. Yet scientists are understandably cautious. A researcher from the University of Cambridge pointed out that while the presence of carbon molecules and the planet's location within the habitable zone are promising indicators, they are not definitive proof of life. The planet's structure, likely featuring a high-pressure mantle of ice similar to Neptune, covered by a thin, hydrogen-rich atmosphere, could still be inhospitable despite the potential presence of oceans. These extreme conditions might render any liquid water either inaccessible or unsuitable for life as we know it. Nevertheless, what remains undeniable is the technological triumph of detecting such complex atmospheric signatures. The method used hinges on a phenomenon known as planetary transit, where a planet crosses in front of its host star from our viewpoint, causing a slight dip in observed brightness. During these transits, some of the starlight passes through the exoplanet's atmosphere before reaching us. This starlight carries with it valuable information about the atmospheric composition, as different molecules absorb specific wavelengths of light. Webb's instruments can capture and analyze these subtle changes with remarkable precision, offering insights that were previously impossible to obtain. Future observations using Webb's mid-infrared spectrograph are expected to further refine our understanding of K218b's atmosphere and climate, and possibly confirm the presence of molecules like dimethyl sulfide. The ultimate objective of these ongoing studies is nothing short of revolutionary: to determine whether habitable exoplanets exist, and, if so, whether they show signs of life. But the telescope's revelations are not limited to nearby exoplanets. In another groundbreaking observation, astronomers using Webb detected complex organic molecules, specifically aromatic hydrocarbons, in a distant galaxy formed when the universe was only about 10% of its current age. These molecules, which on Earth are associated with petroleum, coal deposits, and pollution like smog, were previously thought to be far too complex to exist so early in the universe's history. Their detection fundamentally challenges prevailing cosmological models by suggesting that organic chemical complexity arose much earlier than we once believed. The molecules discovered are not simple compounds like water or carbon dioxide, but rather large molecular structures composed of dozens or even hundreds of atoms. These are among the most complex organic molecules ever observed in space, and their presence in such a young galaxy raises profound questions about the early universe's capacity to foster the building blocks of life. The light carrying the signature of these molecules began its journey less than 1.5 billion years after the Big Bang. A blink of an eye in cosmic terms, considering the universe is estimated to be around 13.8 billion years old. That astronomers can now study this ancient light in such detail is a testament to Webb's extraordinary sensitivity and technological sophistication. Prior attempts to detect organic molecules in ancient galaxies could only establish their general presence, but the Webb telescope allows scientists to map where these molecules are located within their galactic environments. One particularly puzzling discovery is the non-uniform distribution of these molecules in a galaxy known as SPT 041847. The irregularity adds another layer of complexity, hinting at processes we do not yet fully understand. Even more astonishing is that this early galaxy appears to be as massive as our Milky Way, and already harbors stars that have produced as much carbon and oxygen as those in our galaxy today, despite being only a tenth of its age. Such findings suggest that galaxy formation and chemical evolution may have proceeded far more rapidly in the early universe than previously thought. Taken together, the discoveries of carbon-based molecules on K218b and complex hydrocarbons in a primordial galaxy offer a dual perspective on life's potential origins. One grounded in the search for habitable planets in our cosmic neighborhood, the other looking deep into the past to understand how the essential ingredients for life emerged in the early universe. These breakthroughs not only enhance our knowledge, but also provoke new questions about how common life-bearing worlds might be, and how quickly the universe became chemically enriched. The James Webb Space Telescope has fundamentally reshaped how we explore space. With each observation it sends back to Earth, it challenges scientists to reconsider long-held assumptions and entertains the possibility that life, or at least the ingredients for it, may be widespread across the cosmos. The ability to detect subtle molecular signals from planets dozens or hundreds of light-years away, and from galaxies that existed nearly 13 billion years ago, reflects an extraordinary leap in our technological capabilities. These advances are more than just academic achievements. They represent humanity's drive to understand the cosmos at its most fundamental levels. The discovery of carbon compounds in the atmosphere of K218b may not yet prove the existence of life, but it brings us closer than ever before to answering that age-old question: are we alone? Meanwhile, The detection of complex organic molecules in one of the earliest galaxies adds a new dimension to our understanding of cosmic history, suggesting that the chemistry of life was already underway when the universe was still in its infancy. As astronomers prepare for more in-depth studies and await further data from Webb's mid-infrared instruments, anticipation builds. The coming years may well see the telescope unveil more astonishing secrets. Secrets that will continue to redefine not only our knowledge of the universe, but also our understanding of life's potential throughout the cosmos. With each new milestone, the James Webb Space Telescope affirms its role as a cornerstone of space science, pushing the boundaries of what we know and what we dare to imagine. It connects the distant past with the distant future, linking the chemical complexity of the early universe with the atmospheric mysteries of worlds yet unseen. In doing so, it extends an open invitation to continue exploring, questioning, and dreaming. As we gaze into the sky with Webb's eyes, we are not merely looking outward, we are also looking inward, confronting the fundamental truths of existence and our place in a cosmos far richer and more mysterious than we ever knew. This groundbreaking discovery, made by the James Webb Space Telescope, represents not just a leap forward in exoplanetary research, but also in our understanding of the early universe and the potential for life beyond Earth. As scientists continue to study K2-18b and similar sub-Neptune exoplanets, the line between known and unknown worlds begins to blur, allowing our imaginations and scientific pursuits to wander farther than ever before.